So it's a pleasure to have Massimo Tarrona, who will tell us about bootstrapping inflationary correlators in Mellin space. Please.
It's a pleasure to be here, and thank you very much for inviting me and for the opportunity to give this talk. So this talk is mainly based on working collaboration with Charlotte on the Bootstrap in the sitter, and most of it will be based on these two papers here. You can see right my mouse. But I will also try to mention some results that will appear soon in collaboration both with Charlotte and also something work in progress with Shukla and Trivedi. So let me start with some motivation. And let me say that the main motivation to think of Bootstrap in the sitter actually comes from phenomenology, and in particular from inflationary physics. As you all know, the universe we see today is the product of some quantum fluctuations that were happening during an inflationary period. And the inflationary scale sets up an upper bound to the mass of this quantum fluctuation, which is actually very high. It's of the order of 10 to the 14 GeV. So if you could actually measure the imprints of such fluctuation, we would have access to the largest possible collider we could think of. Furthermore, as I said already, quantum fluctuation propagated with time evolution and became what you can see here in this picture. First, they appeared in the cosmic background radiation, and then nowadays they will have an imprint on the density fluctuations that there are today, and are responsible for the large-scale structure of the universe. So it's very challenging experimental endeavor to try to measure such density fluctuations. And today we can only measure, unfortunately, 2-point functions, which it's already a lot. All we know about cosmology comes from the measurement of such 2-point function, which is about 2 numbers. There is the magnitude, which we know is of the order of 10 to the minus 10. So it's something quite small, and then there is a small deviation from conformal invariance, which is parameterized by this parameter epsilon. So yeah, 2-point function is nice, but it's only 2 parameters. In the sky, there is actually infinite amount of information waiting to be measured. And right now, it's a very nice moment because we are far from it, but not so far. We are 1 or 2 order of magnitudes away from the first prediction that we should be able to measure in these higher point functions. And this higher point function I depicted here in some picture, there are, for instance, 3-point function or also higher point function. Here in this talk, I will mostly focus on 3-point functions of density fluctuations. So 3-point functions, as you can imagine, they contain much more information than the 2-point function, and to each of the possible shapes of this triangle, there is some information that one should extract. So it's quite important to understand the shape of these 3-point functions, and our task from this phenomenological perspective will be to classify, in particular, the effects of new degrees of freedom. So far, this type of direction was quite successful. And but it went in a direction of connecting this cosmological application to amplitudes. In this talk, instead, I will try to take a similar but slightly different path. Instead of connecting directly with amplitudes, which somehow is very natural to do because of momentum space, which I will also mention, I will try to actually make a more direct connection with the AdS-CFT and actually conformal field theory, which is also another part of the story which could play an important role. So in this talk, I will actually try to make contact with the AdS-CFT in particular. So just to give a few more details of what type of results we are looking at, and also the relevance of it for this type of cosmological application, the measurement of this 3-point function of density fluctuation will allow us, in principle, to do something very interesting, which I would call inflationary spectroscopy. So basically, the point is the following. So if one looks at this slightly broken conformal symmetry in inflation, one can actually already write down this 3-point function of energy fluctuation in some limit, which is usually called squeeze limit, is the configuration, is the shape in which this triangle has one leg, which corresponds to, let's say, the momentum K3, which shrinks and goes to 0. And these limits turn out to be very important to understand the imprints of new particles, because the dependence on the momenta actually appears in this ratio, K3 over K1. And just from symmetry consideration, one can predict that this has to go to the power IM, where M is the actual mass of some possible new particle produced during inflation. So this is a particular oscillating behavior, which we should actually see nowadays in the density fluctuation of the universe on a large scale. So if we were able to measure such 3-point function, we could do actually spectroscopy of the density fluctuation and read off the masses from the actual periods of fluctuations of the density fluctuations. Of course, 3-point function is not just that. This is a very simple limit where this ratio is, of course, fixed by symmetry, but there are other ingredients. There are overall coefficients, there are overall phases. And the question is if we can understand these phases, what their meaning is, and in fact, if we can actually bootstrap them, and not only in this limit, if we can actually bootstrap the full thing. So this is what we want. This is what we want to do, and this is what I will try to explain. So this is a kind of more phenomenological motivation. But beyond this phenomenological motivation, there is also some more formal perspective to the problem, and some more conceptual question about holography itself. So indeed, as we are all by now convinced and know, quantum gravity observables are holographic. The most famous example of this is ADS-CFT correspondence. And actually, ADS-CFT correspondence is maybe the only example where we really understand this holographic nature of gravitational observables, where this notion is precise. And the reason for this is that at the boundary of ADS, we have a notion of time. So the boundary is time-like. And so we can make sense of quantum mechanics directly at the boundary and understand the observables, and in particular causality, because we have time. And we can understand even non-perturbativity and also unitarity. So as soon as we try to move a little bit farther from ADS-CFT to consider more general backgrounds, still maximally symmetric, like for instance the sitter, which will play a role in this talk, but also flat space, we actually lose this very nice property of having a time-like boundary. In the sitter, we will have a space-like boundary. And therefore, the problem of understanding causality, unitarity, and consistent quantum mechanical evolution becomes not so clear. And this actually was famously dubbed from NEMA, time without time. So the problem is try to formulate actually some non-perturbative bootstrap condition in the sitter, which are right now we don't have. And in particular, what conditions should hold in the sitter for these observables to be consistent with causality and unitarity. So how do we encode on this boundary observable such important conditions that in ADS we know how to encode? Precisely because of this goal that I wrote here, there is a small caveat for this talk. Usually when people talk about the sitter-CFT correspondence, people talk about a wave function of the universe. But the wave function of the universe is not really an observable, right? So here in this talk, I will focus actually on the so-called correlators, which are what will become the inflationary observables. So this is what I will focus on. And this type of correlators will be the subject I will try to bootstrap, as I will try to convince you in the next slides. So the point, let me reiterate it with this slide, is that in ADS, we have a pretty good understanding of what happens in the bulk. We have a pretty good understanding, and very recently, a huge number of technologies have been developed to understand the scattering processes. This goes from spectral representation, Mellin amplitude technology, and so on. They mostly relied on position space approach to correlator on the CFT side. And the question I want to address in this talk is if we can adapt this technology that was so successful in anti-de Sitter to the sitter. And also, of course, what are the limitations of the technology that was successful in anti-de Sitter to the sitter. And in particular, what we would like to do is to consider a map between, to understand if there can be, a map can be written between these objects here, which we understand pretty well right now, and these objects here, up to maybe some analytic continuation, which I will discuss in this talk. Actually, it will not just be an analytic continuation, but something quite closely related to it. And there are some nice observations about this map, which I will discuss. So here you see there is the space-like boundary here, and whatever that is a conformal boundary at future infinity in the system. Okay, so please stop me whenever you want. It's always a bit funny with the Zoom seminars. So if you give me a sign that you are listening, it would be great.
I'm still here, and I think the other.
Yeah. No, but everyone in general. Perfect. So this will be the outline of the talk. So there will be mainly two sections, and the first section will be the bigger one. And the first section is basically from singularities to de Sitter exchanges. So I will review first how one does this in anti-de Sitter. By now, this is quite well understood, and it's also very simple to review. So I will center my attention on the concept of conformal partial waves, first in position space, and then I will move to momentum space. Momentum space has been much less studied also from the perspective of the conformal bootstrap. So it's interesting in its own right to try to develop some better understanding of momentum space for CFTs. And then after having introduced this momentum space technology, I will try to discuss how to write down these anti-de Sitter and de Sitter exchanges. And as you will see, the way the formalism that will be developed with this introduction of this Mellin space approach to momentum space will allow us to deal with anti-de Sitter and de Sitter in a very similar footing. They will actually be almost the same up to some choice of coefficients, overall coefficients.
Actually, Massimo, I have a question.
Yes.
Sorry to interrupt. So from your introduction, it was not quite clear to me, since you didn't write it down, maybe you will. So you want to bootstrap something, but on the other hand, you also have some theory in mind, which has some extra particles and so on. So why are we talking about bootstrapping? Could we also say that, okay, it's just some theory, you would like to calculate some diagrams in that theory? Where's the bootstrap entering? Because sometimes bootstrap enters when the theory is strongly coupled or something like that. But is your theory strongly coupled or is it weakly coupled?
No, I mean, there are various subtleties here. So the point is that it's not that I have in mind a particular theory. That's exactly the point. We don't know what is for instance, from a phenomenological perspective, we don't know what is the particle content of inflation. So one interest is just to bootstrap the possible particles that could be created and to understand the shape of this configuration associated to some new particles. We don't know what particles they are, so we want to understand the shape from just general principle.
But what does it mean associated? So you have in mind some Lagrangian or not?
No, there is no Lagrangian will appear in this talk ever. We just want to classify whatever we can expect in inflation, just from symmetry and consistent quantum mechanics.
But how will you interpret your result in terms of particles if you don't have any Lagrangian? What does it mean then to have a particle?
It's, in this sense, I will discuss a particle as, whatever observable I will compute will have an interpretation as an exchange amplitude, will have some singularity, and that singularity at three level will allow me to interpret it as a particle, contribution of a particle. But mostly it's because there are quantum numbers associated with it. There will be a mass and a spin.
Okay, maybe, yeah, okay, maybe I'll ask my question later.
Maybe it will be more clear afterwards. But there was also another thing that was very interesting about what you asked, is about being strongly coupled or not. So in the usual approach to in correlators, as soon as, there will be IR divergences, and there will be things that we don't understand. We will have to resum infinitely many loop orders in order to get something. So the goal is to also understand this type of resummation, which should be non-perturbative. There should be some non-perturbative physics here that is associated to inflation. And to try to understand some non-perturbative condition that will allow us to understand this resummation will be also an important point, because if we look at just single loop diagrams, there would be IR divergences. So the wave function of the universe is not integrable. So this is also relevant for the question. Anyway, let me try to go into some more details, and maybe also the first question that you asked will be more clear. So in this first part of the talk, I will be very basic, and I will try to review mainly the ideas, and then to try to generalize them more and more to see where we are trying to go. So and this is where I will start from singularity to exchange. So here I will focus basically on the logic that I want to go from the singular. I will not ever use a Lagrangian or ever compute a propagator. I will just try to bootstrap the singularities and then understand how to write down objects that have the right property of being exchange amplitudes. So there are two ingredients and basically two ideas. One, which will play also an important role and already has played to some extent an important role in the context of ADS-CFT, is the ambient space technique. What the ambient space technique will do here is that not only will allow us to use all we know about Euclidean anti-de Sitter space and its possible analytic continuation to Lorentzian anti-de Sitter space. So in the ambient space, Euclidean anti-de Sitter is just this double-sheeted hyperboloid here depicted in blue. But in the ambient space, we can also draw Lorentzian de Sitter. Lorentzian de Sitter is this orange hypersurface here. And then there is the light cone, which is I depicted here, x minus and x plus. And this is the common boundary. So in the case of Euclidean anti-de Sitter, it will be some, in both cases, it will be some space-like boundary, because here I'm considering an ambient space with which is Minkowskian, but it's the common boundary between these two. So using this type of picture, we will actually be able to write down an explicit analytic continuation, an explicit map between the observables that live on, they will both live on the boundary, but they will have an interpretation for the Euclidean anti-de Sitter, and they will have some other interpretation for Lorentzian de Sitter. So this is a bridge that will play an important role. And then there is of course the common mantra that we will also stick to, and that basically singularities will fix everything. And you will see that this will be true actually also in the Sitter. Of course, this is quite difficult. In ADS-CFT and in Lorentzian CFT, we actually understand the non-perturbative singularity. In flat space already we don't understand, and in the Sitter is also quite complicated. So all we can do at this level is to just stick to a perturbative expansion, where we see at tree level we will have single poles, at loop level we may have branch cuts appearing, and so on. But what we are looking for, at least perturbatively, is we are looking for a type of dispersion relations, which will allow us, and we will see actually this explicitly, to reconstruct the full exchange amplitude just from the knowledge of its singularities. Maybe there will be ambiguities, but this is all standard. This is all part of this of the game for this type of dispersion relation. And actually, this type of approach is quite relevant in ADS. So we know a lot in ADS right now in Mellin space about this type of dispersion relations. And it would be interesting if this type of results could be extended also to the Sitter. And to some extent, the result I will present at tree level will play this role.
Massimo?
So, yes, please.
If I may ask, from the answers I see, are you assuming that you have only stable particles in your model, or you also...
So, in the Sitter, everything decays because of time evolution. So the Hamiltonian is time dependent. So everything basically will decay at some point. But you can still discuss this time evolution. You can still try to understand the signature of these particles. So at this level, this will not play an important role. Okay. If the particle is stable or not. But yeah, in the Sitter, because of time evolution, the vacuum is changing and everything will actually decay into...
So the draw you make here is not yet what you will have...
No, this is just the idea. The draw here, the draw I make here is just the idea that we want to understand the singularity structure of these observables. And indeed, we will be able to understand this. We will actually be very precise in understanding this with the CFT language, which type of conformal block will compose this singularity. And we will actually make also precise how from this singularity we will reconstruct the full object, the full observable, full exchange amplitude. So the starting point idea is very simple, but I mean, this is very pedagogical in a sense, and I will review things that for most of you are quite simple, but it's interesting to see this path because this is exactly what we will do in curved backgrounds, but maybe it's less familiar. So the point we want to start from is to identify three-level discontinuities. So in flat space, everyone knows what these are, okay? You take a propagator, you take its imaginary part, you get on-shell leg that is set on shell. But what is this concept? This concept is nothing but the concept of harmonic function. Harmonic function in flat space is something very simple. It's just a leg that is put on shell. That's it. That's what we are looking for a discontinuity. So we want to generalize this concept to constant curvature background. And it turns out that this is actually extremely simple. So the concept of harmonic function can be extended to constant curvature backgrounds using, in particular, this ambient space formalism. And the generalization of this is given by the split representation for the partial wave. So the split representation of the partial wave is precisely the same ingredient that enters into this harmonic function. Just these plane waves are replaced by bulk-to-boundary propagators. And as you see, you have the two plane waves which are associated to these two bulk-to-boundary propagators. And the role of this energy conservation delta function that was setting on shell the internal leg is actually played in this split representation by the fact that you are integrating over the boundary. And you remember the boundary is light cone, so p squared equals to 0, okay? So we actually have the generalization of the concept of discontinuity to constant curvature background. In particular, in this case, I'm working in Euclidean ADS space. And now we can actually forget about bulk. We can actually try to go completely on the boundary, since that's what we are interested in. And it's actually very easy. We take that object, the harmonic function, and we actually connect the remaining two bulk points to the boundary with some other bulk-to-boundary propagators. So this actually ends up in something that is a simple thing, is an integrated product of a CF3 three-point function. This goes under the name of conformal partial wave. And this is the dual object to this harmonic function, which physically we should think as the discontinuity. So of course, this is something formidable. So I wrote it here as an integrated product, but I mean, these three-point functions are known, but they are not easy. So the integral is quite complicated. But, and the question is, how do we read off some physics? And this is where the Mellin approach actually can come rescue us. And this is actually something that was known since the time of Mach. Actually, Mach had this idea. And you can rewrite this complicated integral in terms of a Mellin transform. So you first have to identify what are the independent variables. In this case, it's a conformal field theory object. So it should depend on the cross ratios, u and v. So you have two variables. And if you want to write it as a Mellin transform of something, you need to introduce two Mellin variables. And you write it as a Mellin transform with respect to S and T. And here you see the cross ratios. And all the properties of this complicated integral become geometric and they are encoded into the poles of these functions here. So basically everything all the physics of this function is encoded into the poles of a bunch of gamma functions. So for instance, the simplest thing to see is if you look at the u variable, so you see you have u to the power t, so we have to look at the poles in t, and there are various poles in t, but there are these poles here. You see these two gamma functions in blue and in red, and these poles are depicted here, and you can actually see that there is two contributions of two conformal multiplets. So each gamma functions encodes the contribution of an entire conformal multiplets, one of 2 is tau and the other of 2 is d minus 2l minus tau. So these are the one multiplet and its shadow, basically. So from this Mellin representation, a lot of things about this integral become manifest, and also the quantum numbers of the thing that is exchanged here of this discontinuity are encoded into some polynomial function here of these Mellin variables, which goes under the name of Mach polynomials. That's what Mach polynomials are. That they encode the quantum numbers of this singularity here that propagates inside. Very good. So this is all very this is all very standard, and I just reviewed here basically the idea. And what we want to do is to try to do the same thing, but in momentum space. Now I want to explain why momentum.
Excuse me, may I ask one question?
Yes.
So in previous paper, why do you have only scalar operators in the exchange diagram?
Well, it's just to be for the slide to not make it complicated. But
So,
here you see, I consider the most general case. I'm quite sketchy. It's just the structure, the generic structure of this Mellin representation will contain some pieces which encode, you see, these conformal multiplets, and some other piece which will encode the actual quantum numbers, like spin.
Okay, so you are actually summing over entire spins.
Yeah, in principle, you can consider all possible representations.
Okay, thank you.
You will have an harmonic function for each possible representation. So now we want to go to momentum space. The reason to go to momentum space is twofold for us. One reason is that for the sitter, we will ultimately want to break conformal symmetry. You remember in the first slide, there is this, in the 2-point function, there is a small breaking of conformal symmetry. So in order to break, if you want to break conformal symmetry, it doesn't make sense really to think of, if you want to have application to cosmology, it doesn't really make sense to think in terms of cross ratios, but it's much better to make manifest the translational symmetry of the boundary. So this is why the momentum space is relevant for inflation. But in general, it's also relevant as a matter of fact for the CFT itself. So it would be, and there has been some work about momentum space and the bootstrap also. So let's try to completely mimic the logic here, and we want to write down and understand what will be this conformal partial wave in momentum space. Again, it's something complicated, right? It was complicated already in position space, and we have to accept the fact that it's something that is complicated, but let's try to understand what are the variables on which it will depend and try to see if there is a way we can make sense of it and read off some physics out of this complicated integral. So in momentum space, this object is a 4-point function, so it will be associated to this type of polygon. So as a matter of fact, without asking anything, it will depend on the length of this size, so the modulus of this momenta, K1 modulus, K2 modulus, K3 modulus, and K4 modulus, but there is also, at 4 points, there will also be one diagonal. Of course, we have much more symmetry than translational symmetry only. We have dilatation symmetry, we have conformal symmetry. So dilatation symmetry will actually reduce the number of variables on which this function will depend to just 4, because it can only depend on ratios of these lengths. Once I fix the ratios, everything should be completely fixed. Of course, it would be nice to implement also full conformal symmetry and reduce the number of variables to 2, but this is actually very complicated in a momentum space because there is no analog of the cross ratios in terms of the momenta. So we will stick to a function of 4 variables, and we will see where is the effect of conformal symmetry in the structure of this function of 4 variables. And because we have a function of 4 variables, its Mellin representation will be naturally a Mellin representation in 4 variables. So that will be the first observation. Another observation is that that will allow us to make something simpler here, is that you see this conformal partial wave is actually factorized. It's something factorized. You can actually see the 3-point function here. So if we think of the 3-point function and write it in Mellin space, so you take these external legs and write each leg in Mellin space, what will happen is that you will factor out some overall Z dependence. The Z dependence is in Poincaré coordinates in this Euclidean ADS space. Okay. So if you do that and you do the Mellin transform, you will naturally end up with some delta function of the Mellin variables. So it's actually quite natural to introduce some auxiliary Mellin variables, U and U bar, which are associated to the internal leg. And this will actually simplify a lot, at least the reading off of the physics in this Mellin representation. So what we will do is to therefore consider a function which will be ultimately a function only of 4 Mellin variables, but we will introduce this auxiliary Mellin variable U and U bar And there will be these Mellin space delta functions. And the role of this Mellin space delta function will basically to be associated to these dilatation word identities. So like in translation invariance implies momentum conservation, the dilatation word identities will imply that the sum of the Mellin variables that are entering in a single vertex will always be some constant. So in a sense, what we are doing here is to consider not only the Fourier transform with respect to the external leg, but also some Mellin transform with respect to the bulk coordinates. So in this respect, the bulk of ADS is simply the Mellin transform of the CFT correlator.
Sorry, but aren't these variables complex?
Which variables? S1, S2, S3?
Yes.
You mean? Yeah. But I mean, maybe I'm a bit sloppy. You can define this delta function precisely on the complex line. This is a very precise mathematical identity. So maybe you should write delta of I, S1, S2, S3, so that the delta function is real. Everything is consistent.
But then when you want to do things like the form contours, you have to be careful, right?
Yeah, you have to be careful. But actually, it's Mellin space is actually very good at that. You can actually see precisely. So all these delta function distribution will appear as subtractions. You will need, when you do analytic continuation, you will need to do some subtraction, because when you move the contour, you will pass by poles, and they will, and this delta function will appear. I will actually use this over and over, because, for instance, when we will work with exchanges, we will need to, when we compute the equation of motion on the object, we will have to recover a delta function, some distribution. They will appear, all because we have to be careful about these subtractions. But
usually what you have to do is you have to think of these delta functions as some contour integral that surrounds some pole.
Yeah.
This is the correct way to think about it.
Yeah. Yes.
Because otherwise, it's simply not analytic. So you cannot deform any content, right? These delta functions would only hold for the real part or for the imaginary part of these parameters. So.
Yeah. You have to be just careful about this, but you can work with it. In the end of the day, this delta function will always be removed. We will always replace this u in terms of the other variables, but it's very convenient to keep this u and u bar to understand all the possible properties of these complicated functions.
Also, so since you're talking about Fourier transform, don't you have to worry about things like signature and ordering?
Yeah, it's all space-like at the boundary. So there is no, for the Fourier transform, there is no problem. We will have to deal with these issues on the Z variables. I will explain this, because we will, when we will move from Euclidean anti-de Sitter to de Sitter, we will have to perform an analytic continuation in Z, which is the bulk coordinate that will become conformal time in de Sitter. Okay. Any other question? So yeah, I mean, you have to be careful. And indeed, there will be many things that, if you are careful, will come out, and we will even discover other things. This will actually enter the last part of the talk, where I will discuss, for instance, word identities and consistent interaction of partially massless fields, which is something that people simply haven't yet studied, but is very relevant for de Sitter. And it all will come out very naturally from this Mellin representation. So all the word identities, everything that for massless particle and new results for partially massless will be all manifest here. Just have to be careful and do things properly with these complex integrals. And then let me introduce the last ingredient, which actually will show you why there is some simplification. I mean, it's a complicated integral. It was a complicated integral before, but at least has a geometric meaning. And so what I want to say here is simply that where are the poles? And the location of the poles is what is the translation of conformal symmetry. So for each leg, external but also internal, there are basically two series of poles. That's the rule. And these two series of poles I depict here in the case of a principal series. So nu is some real number, let's say. So we have these two series of poles which correspond to delta plus and delta minus, the field and the shadow. And they will always be impaired. There will always be these two infinite series of poles for each external leg. So in the end of the day, is a Mellin representation with just products of gamma function and very simple structure of poles. So this is the object we want to deal with. And now I want to try to go to try to understand how to go from here, from the discontinuity, the conformal partial wave, to the actual exchange amplitude. And you will also understand why it's useful to introduce this U bar Mellin variable for the internal leg. So to do that, just to be a little bit simpler, let me drop off the external leg. You can actually attach them very easily in momentum space. Let me describe the basic structure of this complicated function. So in particular, let's take the propagator, the object that will be the propagator for a particle of mass m and spin j, as a Mellin representation in terms of these u and u bar Mellin variables, which are the internal Mellin variables. So there are various ingredients. The first ingredient is the place where symmetry is. So symmetry fixes the conformal partial wave. So this omega is nothing but the Mellin representation for the conformal partial wave. So this will be something that will be there. But in order to write down a propagator, we need other two things. We not only need to impose symmetry, but we also need to impose a boundary condition. And we know in anti-de Sitter there are two types of boundary conditions. There is a Dirichlet and Neumann boundary condition. So what is how do we implement these boundary conditions in using this format? Actually, this is quite simple. And indeed, you remember we had two series of poles. What we need to do is to simply put a 0 for each of the wrong poles that we want to project away. So we just can write down some projectors which will actually contain such zeros, and we cancel all the unwanted poles. So that depending if you cancel the poles on the top or below, we get Dirichlet or Neumann boundary conditions, which are associated in the end when we consider a boundary expansion to the standard z to the delta plus and z to the delta minus modes. Okay, so this is actually quite simple. There is some similar procedure you can also do in position space, but it's just about this project.
Actually, Massimo, I have some questions. It's getting a bit technical, but yeah, in the end, you're just computing here for us in some complicated Mellin way and so on, but there is this Witten diagram that you're computing, which is just a three-level exchange of a certain thing. Now, it means that behind there is actually a Lagrangian which describes this massive particle coupled to other particles.
Yeah.
And so you said there's no Lagrangian, but there is this Lagrangian from which this diagram came out. Now, why is this the right Lagrangian to consider? You know, there is a ton of other things, conformally invariant objects that you can consider, and we do consider in conformal field theory. There are actually, we usually call conformal partial waves something else, not what you call here. There are Witten diagrams, there are conformal blocks, there are shadow blocks, there's like a ton of different things. Why is this the right thing to consider?
I mean, what I'm trying to say is that the result, this type of result, is basically fixed up to some ambiguity. We can parameterize the most general thing that we can have that is constrained by symmetry and consistency.
Well, so, I'm sorry, because you have decided to consider the Witten diagram, if you considered some other conformal invariant object, you would get a different result.
So your question...
Any function of U and V is conformally invariant. So why is this the right function to consider?
Yeah, I mean, here we are starting from this singularity. So we want a certain type of singularity which we associate to some three-level exchange.
Okay, but...
It's just three-level approximation.
Okay,
and we want to have everything we can write at three-level. Of course,
if you just have the singularity, you can add any other piece on top of the singularity, which does not have the singularity, and that other piece that you can add is not fixed by your considerations.
Of course, yes. Everything that is not singular is the standard contact. I mean, everything here. I mean, maybe I'm starting from something that is well known. Of course, in anti-de Sitter, everyone knows how to compute.
No, I just wanted to point out that there is a Lagrangian behind all your things, which is the Lagrangian from which this Feynman diagram was derived.
I totally agree. Here at three level, there is a Lagrangian. And you can actually maybe show, I mean, there is nothing else because it's basically, if you want some effective theory, if you have these quantum numbers, you can always write a propagator which comes from a Lagrangian. I agree. Just the point is, if you have a Lagrangian, you want to compute the propagator, it's complicated, right? for a massive spin. So you shouldn't start from a
It is
Lagrangian.
complicated, but there is a difference of principle to say, okay, here's some diagram which forms from Lagrangian, I just want to compute it. That's one question. And another question is, I want to bootstrap something from general principles.
Yeah.
That's a different
way
of asking the question.
So the point is, maybe, I mean, I of course agree that here I'm looking at some tree-level object. So it's some very specific type of thing that I want to compute, and which can be computed from a Lagrangian too. Okay, but and of course I also agree that in anti-de Sitter it is all well known. So why you are saying why you are doing this complicated calculation? The reason I'm doing this path is because I want to do the de Sitter calculation, which is much more complicated.
Okay.
So I
just wanted to clarify if there is Lagrangian or not.
Yeah. There is, in this case, in all these cases, you will actually be able to write an effective Lagrangian for these couplings.
Okay.
Okay, and this will be the exchange amplitudes coming from this effective Lagrangian.
Okay.
Yes.
Thanks.
Yes. Okay. So, and then the other ingredient. So I'm just trying to introduce in the simple setting of anti-de Sitter the main ingredients. So there are the symmetry, the fact that implements basically factorization, which is this harmonic function. I will reiterate. Then there is the boundary condition, which enters here, and then there is another piece. And this piece, which appears here as a bunch of poles, you see these red poles, it goes from -infinity to +infinity. This is kind of geometrization of this complicated function. This bunch of poles is associated to the fact that when we want a propagator, we actually want to generate a delta function singularity after we act with the wave operator. And this is actually the way this singularity will be encoded with this type by adding this type of pole. So it will actually generate precisely this. And in this Mellin space approach, they will turn out to be very related. It's basically like inverting the discontinuity. So a discontinuity with respect to the internal momentum k will precisely cancel this cosecant function because it will bring about some sign, and the cosecant will be canceled. So there is some simple, although this is complicated and it's quite technical, I understand, there is some simple ingredients entering this propagator. And they all have a simple meaning. And now, so all I've said so far, I didn't need it to do like this. It was already known, it was about anti-de Sitter. We knew how to compute a Witten diagram for long, but I explain it this way because this way we put this calculation on the same footing as the de Sitter calculation, which is actually new. So we want to go to de Sitter now. So going to de Sitter introduces various a couple of issues that we have to deal with. So the starting point, we still want to be the conformal partial wave because that's the singularity we want from the exchange. So the exchange must have that type of singularity. That's our requirement for the bootstrap problem. So we want a single particle, something that has the singularity of a single particle. But now we have to impose consistent type evolution, we need to impose causality, and we have to do this analytic continuation from this Euclidean anti-de Sitter space to de Sitter. So the analytic continuation is something of this type. So basically Z will be related to the conformal time up to some factor of I. Now, the path that you analytically continue from Z to eta will basically encode the time ordering in de Sitter. And then, because we are interested into in correlators, we need to remind that there is, so here you see there is the in contour. And in contour goes from -infinity to 0 back to -infinity, but the time ordering is different on the different branches. So we need to separate all of this contribution to the in contour. There would be plus contribution, minus depending on the type of time ordering that we have, plus minus contributions, and so on. And we have to do that. So in order to do that, we have to first divide the conformal partial wave into two pieces, which will correspond to different ordering, depending if Z is greater than.
I'm sorry, Massimo, I have another physics question.
Yes, sure.
So this de Sitter physics is when you do this analytic continuations. So I just wanted to make sure that So in de Sitter, of course, there are various different types of de Sitter. There are various slices of de Sitter. There's global de Sitter. There's a patch. There's this. There's that. There are a ton of different vacua. And some of them are physically completely irrelevant, and people have a lot of confusion constantly, talking about all sorts of nonsense and stability of de Sitter. So when you do this analytic continuation, what would be the actual physical system
I'm trying to compute a fixed time correlator at this future time like infinity. So
in which slicing of de Sitter?
Is the Poincaré patch.
Okay.
So this is what I'm interested because of this inflationary application. So I really want to consider the full time-like boundary. So I am in that patch.
Okay.
And I want to compute the fixed time correlator. So to compute that fixed time correlator, I need to introduce this in contour. And I need to analytically continue on all these branches of the in contour.
Okay, but if you were like to write down this effective theory that you say is behind these things that we are computing, that effective theory would be in what vacuum state? Like
yes, this is important. It would be in the Bunch-Davis vacuum.
Okay. Okay, thanks.
Yeah, this is very important. Yes, thanks for mentioning it. Actually, I wanted to mention it. Actually, I will also mention these other more crazy vacua, the so-called alpha vacua.
Yeah, but I don't care about them. So.
But yeah, many people don't care for good reasons. But they still, it's still good to mention them sometime. Anyway, yes. So this analytic continuation and these rules of analytic continuation will be tuned to work on the Bunch-Davis vacuum. Okay. Very good. So we do this splitting. We do this analytic continuation, and what will happen is that from the conformal partial wave, we end up with these two pieces of the conformal partial wave which have a certain time ordering or anti-time ordering, and they will be dressed with some phases. So the good thing of Mellin space is that it allows us to actually read off these phases very cleanly. And these phases cannot be fixed, of course, by conformal symmetry. That's where the information about consistent time evolution and the Bunch-Davis has been appears. And then we can...
Sorry, does that mean then that this result does not follow uniquely from analytic continuation? Is that what you're saying?
Yeah, I'm imposing Bunch-Davis.
So you can analytically continue to get each of these separate pieces, but then you have to combine them in this non-trivial way.
Yes. I mean, this is how the in contour is defined. So you have to be careful about the analytic continuation on that contour.
Okay.
You have to be careful about that analytic continuation to define this analytic continuation. You can do a similar thing for other vacua, and you will get different results. I will explain. I will mention that what will go wrong if you do this for other vacua. What will be the difference? It's quite striking. Why Bunch-Davis is so interesting. You can actually make it in some very generic condition on the CFT correlator. But this will come later in the talk, so I don't want to anticipate it. Okay, so let's come back to the propagator. I've done this analytic continuation. I can do it for a different, here I will stick to the propagator just because it's a little bit simpler to discuss. Of course, these are, there is some technicalities, but the ingredients are the same ingredients as in anti-de Sitter. So I have done the analytic continuation of the propagator on all these possible contours. I have the same pieces. There is the cosecant factor, which actually encodes this delta function singularitY. The EFT is the contact term in the propagator. Then there is the boundary condition. Now there will be both boundary conditions. Of course, in principle, in the Bunch-Davis, you don't expect to be either Dirichlet or Neumann. It will be some superposition of the two. And they will be a certain boundary condition for each of the plus minus contour. And then there will always be the conformal partial wave analytically continued to the in the proper way. So the summary is that using the Mellin-Barnes representation, there is a dictionary for this analytic continuation. And this dictionary is general. It's just holding at the level of these three-level diagrams. You can actually, it's actually more general. So for each internal leg, you will just get this bunch of phases times the Euclidean IDS harmonic function. And for each external leg, you will get this type of phase times the Euclidean ADS. So we have a basic dictionary that allows us to go from Euclidean anti-de Sitter to this Bunch-Davis vacuum. And you can do it for internal legs and for external legs. So this comes from all this discussion that I mentioned here, where we impose this Bunch-Davis. And then we have to combine everything. And that's where the magic of Bunch-Davis will come out. So here I will just consider I will not consider, I just dropped out the cosecant for a second. This is the basically the discontinuity of the exchange, is the discontinuity after this analytic continuation. You will have a certain discontinuity for each of these contour pieces. There will be the coefficient. This is nothing new. But when we consider the harmonic function, we have to do the analytic continuation of each of the legs. So we'll have a bunch of phases here. So the important thing of Bunch-Davis is that all of these phases, you see, all of these Mellin dependence in the harmonic function always enters as a sum, S1 plus S2 plus U. So this sum, which was constrained by the dilatation word identities to be a constant. So if I say it like this, it's a bit technical, of course, but the point is that all this analytic continuation just gives you an overall OP coefficient, which is a constant. It does not depend on the Mellin variables anymore. So what does this say? It tells us that one can simply expand the Sitter exchanges in Bunch-Davis in terms of actual ADS exchanges. So there is, because of this cancellation of the Mellin dependence, there is a complicated functional relation which allows us to write the de Sitter exchange as a sum of anti-de Sitter exchanges. Let me mention this, what happens instead if we don't do the Bunch-Davis, but we do this more funny alpha vacua. I don't know if everyone knows about this, the existence of this other vacua, but in de Sitter, the Bunch-Davis is just one of a one parameter family of vacua, which go under the name of alpha vacua. And if you impose, if you consider alpha vacua, what happens is that these two boundary conditions are not sufficient to describe the propagator on the alpha vacua. You need to consider two more projectors. So each of these projectors, Dirichlet or Neumann, was coherent. So U and U bar were projected on the same pole. So you were removing the same representation from both pieces, from both bulk-to-boundary propagators on the internal leg. But if you want to write down an alpha vacua propagator, you have to do it plus minus and minus plus. So this is something that doesn't have a clear ADS meaning. And the reason is that all of this introduces some funny folded, they are usually called folded singularities. They are singularities that are incompatible with standard CFT axioms. So they are not singularities that are just OPE singularities in Euclidean. They will be more crazy singularities. And therefore we never have them, we never see them in the context of Euclidean anti-de Sitter space. But in principle, you can write down these projectors and you can write down the propagator on the alpha vacua as a sum of these, of two ADS propagators plus some other crazy functions which have these singularities.
Sorry, can you
Yes.
maybe say, because I'm not very familiar with this, what the physical relevance of these other alpha vacua that are not the Bunch-Davis vacuum are?
So, I mean, as far as Slava was saying, not everyone considers them physically interesting, all these alpha vacua. As a matter of fact, they exist, but because of the folded singularities they have, they are considered to be unphysical. I mean, if we were in alpha vacuum in the inflationary correlator, we would see some singularity. There should be some divergences. So it's a little bit, I wouldn't know what is physical about these alpha vacua, apart from the fact that they exist. You can write them down. They would be excited states. So the Bunch-Davis vacuum is a vacuum at minus eta equal minus infinity, but the alpha vacuum will be an excited state at that level. So you are not in the vacuum when you go backwards in time. Basically, this is the interpretation that you can give to this alpha vacuum.
Okay, thanks.
It's basically not a vacuum, it's just some state invariant under the de Sitter isometries, but okay.
Yeah, it's some state that is not in the vacuum and will give rise to this singularity structure in the correlator at future infinity.
But you can sort of go between those different alpha vacua, or are they like super selection sectors?
There should be, I think there should be some super selection sectors, but I'm not really an expert about this these alpha vacua. I've been more focused on bunch Davis. So I don't know if people have addressed this question, this type of questions for the alpha vacua actually, if there is super selection sectors or not.
Sorry, can I ask a question
Yes.
about your delta plus minus? Maybe you mentioned it. Do they satisfy a reality condition, or they?
You mean these deltas?
Yeah.
So at this level, I write delta plus minus. I could have wrote, for instance, the spectral parameter nu if I am on the principal series. Most of the discussion we do is always on the principal series, and then if you want to apply it to discrete series or other representation, you have to kind of do some analytic continuation from the principal series.
Great, thank you.
So on the principal series, everything is very nice. You have these two series of poles which are separated. One is up, one is down. If you do some analytic continuation, this pole can mix, and there can be pole pinching, and there can be all of these sort of singularities. You can actually be very precise, study all of these singularities, but it's quite technical, so I haven't I will not mention any detail like that. But you can consider also deltas that are not on the principal series. At this level, it's not even important that, I mean, you can also consider things that are non-unitary. Indeed, if you will go a loop level in principle, you will generate some anomalous dimension which will go away even from the principal series. We will change the d over 2 to some d over 2 plus delta something, some real number. Okay. And now, so I have discussed basically the structure of this singular piece, which fixes the exchange, and then I would just want to say that you multiply the Mellin representation with this cosecant factor just to obtain the full exchange amplitude. So we basically have solved this toy problem of Bootstrap, is requiring factorization, conformal symmetry, and boundary conditions. We have been able to constrain these complicated functions in a simpler way than actually using the Lagrangian. Actually, no one has done it, has ever done it, I think, with starting from a Lagrangian, because the propagator is extremely complicated. Very good. And yeah, and both ADS and the CPW.
So what do you mean that no one got it from the Lagrangian? I mean, how is it what you're doing different from the Lagrangian approach? I don't understand. You compute the propagator; it's a free propagator.
Yeah, but
that's because you impose the free equation of motion. So, I mean, what's
well, if you want to consider a spin J field, I mean, going from the Lagrangian to the propagator is complicated. That's what I'm saying.
Yeah, but at the end you have to. I mean, the way that you're fixing this is at some point you are implicitly imposing the free equation of motion, right?
Yeah, yeah. But what I'm saying is that when you write down a propagator, you are implicitly considering a lot of contact terms, and which are required by the consistency. Here I'm more, since I'm bootstrapping these singularities, I will just focus on the singularity, and the contact term ambiguity will play a role of shuffling around this contact. You're
talking about the exchange.
Yeah.
For the propagator, there's no ambiguity.
Yeah. I'm talking about the exchange. Yes, exactly. Okay. So, and then this is the
problem in principle is well defined. You know, there is this diagram, we have to compute it.
The problem is well defined. It's just about.
You can compute it one way or the other. So you're saying your method is better than the other methods. That's basically your question.
Let's say I'm saying that my method allows, is simpler.
Okay.
It's the same thing. I will actually make contact also with the same problem in anti-de Sitter.
I just don't understand. It's simpler than what? I mean, what would be the alternative? I just don't see what.
Take the Lagrangian, compute explicit.
Well, no, but okay, what do you do from the Lagrangian? I mean, you just write out some vertices with the propagator and you do some integrals. This is what you've done, no?
Well, you have to start for a massive spin J field. The Lagrangian has a huge amount of auxiliary fields. Is the Single-Hagen Lagrangian.
Yeah, so there's the propagator, indeed, the 2-point function for spinning fields in ADS. it's complicated, but you can fix it in a similar way to what you've done here. But then when you actually want to compute an exchange diagram, yeah, you're just gluing some pieces together. So, and again, I'm not sure. So you're saying that fixing the 2-point function would be difficult if I just try to solve the equation of motion by hand. That's what you're saying?
Yeah, if you just, yeah, there are some technicalities. The point, what I'm trying to say is that, you know, in order to write, it's already complicated to write down a Lagrangian for massive spin J field. And that's what you shouldn't do that. Because the Lagrangian is what actually implements all these conditions that I can just write down, bootstrap from scratch. So it's about, maybe if you want, is a logic. Is a logic. Yeah, maybe.
I think the word, use the word bootstrap here is misleading. I mean,
it could be.
You're just fixing the propagator, then you do some integral. I mean, it's not bootstrap. It's not bootstrap. It's just doing some integral.
Yeah, I mean, we are imposing the consistency conditions on this singularity and getting the only functions that satisfy these singularities. You can call it the way you prefer. We are just trying to understand what is this complicated function, imposing that here there must be a singularity corresponding to a mass M and spin J field.
Yeah, so usually the difficulty is that you say that you have this complicated Lagrangians because basically you want to extract out the non-trivial propagating spin J mode from all the other lower spin stuff that usually you put into a field. And you're saying that you are removing this stuff basically by imposing that in a harmonic space or wherever you only see a pole.
Yeah, you just
corresponding to this spin.
Easier, if you want, it's a very simple, it's a much simpler problem than a full-fledged bootstrap problem for a full correlator. But it's simply saying, I want a function that has this singularity.
Sure.
And I want to understand if I can fix this function and what is the ambiguity on this function. That's the problem.
So basically you took the ADS result, which was known, and then you figured out how to do this analytic continuation. That's the idea for the propagator.
That's the idea. That's the idea. We figured out how to implement the consistent time evolution in De Sitter via this analytic continuation on the Bunch-Davis vacuum. Okay. And so we could write this De Sitter propagator, De Sitter exchange, which was not known. So, and the final result is actually a functional identity. So you have this object which satisfies all the consistent time evolution in De Sitter, is the De Sitter exchange. And you can write it down as a sum of two anti-De Sitter exchanges, which with delta plus, delta minus, and some OP factors, which has these sign factors. So in the end of the day, the result is very simple. It's what one should expect. And let me make some comments here. So actually, this is the unique thing that you could write if you would impose a consistent OP limit. Suppose someone handed you the OP limit in De Sitter, so what should be the OP coefficient of an exchange in De Sitter, and Euclidean single valuedness. Why? So because if I impose these two things, I just get this function. This is the only thing with that singularity, with that OP limit, and the Euclidean single valuedness. Actually, our result shows that the Bunch-Davis vacuum, the exchange in the Bunch-Davis vacuum is Euclidean single valued. So this is something that is some very simple thing that was clarified by this result.
So sorry, so let me see if I understand again. So yeah, basically you are writing the 2-point function as a sum of, well, there are these two modes, the delta plus and delta minus, as usual. Usually in ADS there's only one propagating, but you have to include two. Yeah. And so, and then you have to, yeah, so that's you need to dress the 3-point couplings to these modes by these factors.
Yes.
But why do you need to work in momentum space? I mean, isn't this completely general? Couldn't you just be in position space as well?
Yeah. That's my next comment. So we derived this. We did the calculation in momentum space because in momentum space it was simpler to impose this consistency of the analytic continuation. I mean, how do you fix these sign factors in position space? I mean, it surely could be possible to proceed also in position space, but this result, as I wrote it here, it also in position space. So nicely, a byproduct of what we have, I think I wrote it here. Yeah, We also have the de Sitter exchange now in position space. It was known in position space before. I mean, it's just about understanding this type of exchanges. Everyone, people have worked in momentum space, but because of this relation now we know everything also in position space. But not only, we can also write down a spectral representation now. We can write down Mellin amplitudes. The Mellin amplitude that we use to write down anti-de Sitter exchange now we can write also for de Sitter. And not only, we can also understand, since it's single valued in Euclidean, we can also consider a crossing decomposition.
But I mean, the non-trivial physics here is it's in the spectral content, so you have to know where these deltas are valued.
Yeah. But
so the scaling dimensions of both of the internal fields and the external fields.
Yeah, you can choose
continue them somewhere.
Yeah.
Sorry, guys. Maybe we should postpone that to the question session because we're already getting over time, and I hardly see the talk finishing. If
I don't know. Actually, I don't have a clock here. Yeah. I don't know how much time do I have.
Well, there was a lot of interruptions. So, but yeah. Could you finish in 5 minutes also?
Yeah, I think I can. Yeah. Then the other thing I wanted to mention is to understand this sign factor. Actually, they are quite related. At this level, this is just an observation. So we have some Euclidean correlator. We could. Is there a way to understand these funny sign factors? And actually, similar sign factors appear also in the double discontinuity of conformal blocks. Here, these sign factors are just coming from this interference effect from these different parts of the inning contour. So this sign factor arise simply from summing from the contribution of the 3-point function from the plus and minus contour. In the double discontinuity, the usual story with the double discontinuity, you do the right analytic continuation to go to Lorentzian CFT, you get similar sign factors, but there is an important difference. See here, if you have a G delta plus, and you consider the discontinuity in the S channel, you get delta minus. Instead, in these sign factors, you have delta plus. So you have exchanged this dimension. So in the end of the day, if you just thought, let me take this Euclidean single valued correlator, try to compute the double discontinuity and see what I get, you will get that all these sign factor will just come overall, and you will get that everything is just proportional to the conformal partial wave. Because simply the two sign factor will become the two different sign factor after the double discontinuity will become the same product of 4 sign factors. Okay, then, yes, there is a couple of comments about the fact that we can use the you can understand now the spectral representation of these de Sitter exchanges. So the difference between de Sitter exchange and anti-de Sitter exchange is mostly about this non-normalizable piece that will appear when considering, for instance, delta minus exchange amplitude in anti-de Sitter. And in the end of the day, you will get some spectral representation of this sort with these sign factors multiplying. Then one can also write down Mellin amplitudes for these exchange amplitudes. Simply, you remember, this is the expression for the conformal partial wave. It contained both representation with twist tau and d minus 2L minus tau. So if one projects away one writes the same equation, but you get the Mellin amplitude for the exchange. And we can write down now similar Mellin amplitude for the de Sitter exchanges. And also, because we have a single valued Euclidean object, it makes sense to study crossing the decomposition. So yeah, this is a generic basic things about crossing decomposition. And here I want to make a connection between these recently introduced cyclic Polyakov blocks, also called Regge blocks, which are the simplest objects that you can write, which have some crossing symmetry and also are single valued. And one can consider them, of course, in anti-de Sitter very recently. They have been proposed as a basis to expand correlators in CFT, which are single valued. And one can then consider the crossing decomposition and obtain all of these nice coefficients, which have some interpretation as functionals. And you can do the same thing now also in de Sitter. Of course, the physical interpretation of this type of decomposition is unclear at the moment. Maybe it will be clarified in these papers that will appear soon. But the main ingredient, the main functional dependence on this coefficient is actually the same as in anti-de Sitter. There would be a piece which is given by this complicated 7f6 hypergeometric function and some non-analytic contribution in spin, which is produced by this polynomial. Okay, since I'm running out of time, I wanted to mention something about constraint on partially massless particle, and I think I can just summarize it very quickly. So basically the point is that with this Mellin space technique, we can analyze, we can take a decomposition into helicities, and the consistency of the different helicity, the fact that some particle is massless or not, is simply associated that a certain helicity contains or not E-total singularity. The presence of E-total singularity means bulk. If there is no E-total singularity, this is just a boundary terms and will encode word identity. So by studying these word identities in Mellin space, we can actually obtain the boundary terms that appear. And so the actual Takahashi word identities for each of these coupling and partially massless coupling consistently. And then we can apply this to 4-point function and recover in the standard case, j equal 1, we recover charge conservation, nothing new. J equal 2, we recover equivalence principle directly in de Sitter. We can apply also for arbitrary spin, which is something that in de Sitter at least was never done. So by requiring the cancellation of this E-total bulk singularity, or showing that there cannot be any such cancellation, we can actually prove that there is no consistent local theory, effective theory of massless higher spin, and you can actually extend this also to partially massless effective field theory. And okay, so I just summarized very briefly this part of the talk, and let me conclude by saying, okay, this is the bottom line that I try to explain in this talk. There is this nice decomposition, and okay, there is plenty of different future directions, and the most natural future direction to look is loops. And as you may imagine, all of this type of this analytic continuation, they can be done at any loop order. So this type of relation between de Sitter and anti-de Sitter correlators can be written down in general at any loop order. So we hopefully will be able to put out this soon with Charlotte and extend this type of relation between de Sitter and anti-de Sitter correlators beyond 3 levels. It would also be interesting to clarify the potential role of cyclic Polyakov blocks in de Sitter, and of course understand this type of map between de Sitter and anti-de Sitter to have a different handle on these IR divergences in correlators, and also to understand de Sitter unitarity. So at this level, we have seen unitarity at 3 levels, the singularity. So actually, this relation can be thought of some optical theorem, as some type of optical theorem at 3 levels. So it would be interesting to extend this type of thing also beyond 3 levels. And yeah, as future directions, since we are basically talking about how to implement conformal symmetry in momentum space, there are various other type of applications, like also flat holography and celestial amplitudes, where one in principle could try to use some similar Mellin space approaches. I think I can conclude here, and thank you very much for the attention.
Thank you, Massimo. Let's thank Massimo if you want to unlock your microphone. I guess there will be questions or comments. So who is wants to know? Yeah, Andrea.
About the loop amplitudes. So do the loop corrections of these correlators, are they written as operators acting, differential operators acting on the 3-level correlators, or how do they? What's the?
It's simply a relation, a generalization of similar equation like the one I put in the slide. So you see here you have a certain 3-level de Sitter amplitude. It's written as a sum of 3-level amplitude in anti-de Sitter with certain propagating degrees of freedom, delta plus and delta minus. So you will have a similar relation. Let's say you have this type of Candy diagram. You can write it as a sum of 3 Candy diagrams in anti-de Sitter with the delta plus, delta plus, delta minus, and delta plus, delta minus with certain overall coefficients. And this type of relation can be written at any loop order. It just follows from the analytic continuation.
But aren't these diagrams all divergent?
So there will be divergences. There will be IR divergences, UV divergences, and the point is precisely
UV is fine, but
we
IR, how, I mean.
Yeah. The point is to use, so these relations are functional relations that we can write down, and then the point is to try to understand for, let's say, take a light field, try to consider analytic continuation and see how these divergences appear. I mean,
incidentally,
which divergences? I mean, are you taking massless propagators or massive propagators?
Yeah, you can take massless propagator, for instance.
I mean, you can, but should we take? What's the point?
Well, you have a functional relation. You can try to understand using the Mellin representation. You can see all the singularities. You can understand if there is any singularity. And
no, but what's the physical meaning of these massless particles in De Sitter?
Yeah, I mean, it depends on your. You must have a certain model in mind, right? If you have, if you want to think of some inflaton, or if you want to think of some light field propagating De Sitter to understand IR divergences, or.
But I mean, even the Mellin representation. How do you know the Mellin representation exists? I don't understand. Because to go to the Mellin representation, you have to do some integrals.
Massless.
These integrals, won't they blow up?
Or
put it another way, the Mellin representation, it has some, again, it's some contour integrals, and it's well defined when the real parts of the Mellin parameters lie in some range.
Yeah, of course.
Dependent on the external dimensions, but now your external dimensions are complex.
Yeah, they can be complex. You can set them real. You can try to, I mean, I understand. There is the question, and maybe these Mellin representations don't exist, but you will just see. It's just a question of principle. If you want to compute some certain loop amplitude in a model, in a physical model that you are interested in, you should study this analytic continuation to that model and see if this function makes sense. And if you need some subtraction to define the Mellin representation, I mean, maybe I didn't understood the question. So
the question is, how do you define integrals which make sense, which are not infinite? So you can define some Mellin representation, but then if the integrals never converge anywhere.
So, I mean,
for an actual CFT, we know how.
This integral we have computed in many examples, like conformally coupled scalar, massless scalar. They all make sense.
For which values of the external dimensions?
We have done various examples in the simplest cases, like massless discrete series. Usually the discrete series will give you some divergences because you will have pole pinching. Otherwise, if you don't have pole pinching and divergences, there is no problem, right? So you can see where this integral may stop to converge, and you can actually compute and match with everything other calculation. And we have done that in all examples that are known, actually.
So when the external dimensions are in the principal unitary, you say all these integrals, at least at tree level.
Yeah, there is no pole pinching. There is no pole pinching on the principal series, yes. And the problem can arise when you go to the discrete series. The discrete series, the 2D series of pole will be on the same line, and there can be pole pinching. You can actually study this pole pinching. You can actually match with all the result of Maldacena. Everything has been done in the Sitter, and you will recover.
But when you exchange a physical field, I mean, what is the range of delta contained in the physical field?
So you are asking what is the condition on the dimension for?
Yeah, in the spectral representation of the propagator, are you only integrating over the principal series, or are they also? No.
So if you write the spectral representation, I always only integrating on the principal series. For instance, in the spectral representation. I mean, you see here. You have IDS exchanges. We know everything about these IDS exchanges.
No, but again, the point is when you arrive at this, the process by which you arrived at this.
Yeah. Of course, we did it for a case of high mass. So if taking the Sitter, something that is on the principal series, it just means that it's a very high mass. It's a unitary representation in the Sitter with a big mass. And for this type of setting of poles, there is never pole pinching. You can look at the singularities. And the question, of course, is very interesting if you can analytically continue away from this setting. And we did it. We did it in many examples. And at least so in the paper that is out, we did it at 3 level, and it was we were getting exactly the results that you would expect. But there is of course a subtlety in principle of analytic continuation.
Is there other question? If not, maybe, I mean, considering what...
Can I ask a question?
Yes, sure.
So for ADS case, people say bootstrapped, bulk higher spin, cubic, and chaotic coupling by the method you described. Can you do the same, say bootstrapping, bulk higher spin interactions from your method?
There is not, I mean, cubic is just a classification of 3-point functions. This is known for fields for some time.
Chaotic people had non-local interactions.
Yeah, I mean, that's what I tried. Unfortunately, I didn't have much time. So we considered this type of diagrams. See, with one external spinning leg, which could be massless or partially massless. And we considered the consistency with the word identities of this object. So when you look at the various helicity components, so the lower helicity components, depending on if it is massless or partially massless, should not contain any bulk point singularity, which is any total singularity. So by looking at this total singularity, we are able to constrain the contact terms that should appear in this exchange amplitude, so that when you look at that helicity component, there is actually no bulk point singularity, no total singularity. Sometimes it's impossible to cancel all the total singularity. So this is a violation of the word identity, because that helicity component should just be some boundary term. It should just be constrained by the word identity and cannot be any bulk singularity for it. When this happens, you have a constraint on the possible coupling. So basically, we recover charge conservation equivalence principle in this way, and we can actually prove that in local effective field theory, you cannot have massless or partially massless interactions, also in the sitter.
So you can write down explicit non-local vertex?
We didn't try to write down a non-local vertex, but the point is that you see, once you have a complicated function of ET, which is arbitrary, non-local, you can always do whatever you want. You can always subtract anything. The difficulty is to try to remove this singularity with something local. That's what's non-trivial.
But this was also happened in ADS case, no?
Yeah, but in ADS, I mean, we didn't, it is similar to what happens in ADS case. The novelty here is for partially massless fields, which in the sitter are unitary. And so it's relevant to study the consistency. In this case, you see, I have a matter coupling. So I have a gauge field coupled with scalars. So I'm studying the consistency of that particular coupling. Of course, that particular coupling may be zero. Just that coupling is zero in some theory. So we cannot say more than in a theory where that coupling is zero, because we have only looked at the consistency of that coupling. That's the matter coupling. So if I want to couple to matter some higher spin multiplet also with partially massless fields, I would end up with this type of problems. But maybe I don't have to couple to matter, and so we don't know. But that's the statement.
Okay, thank you.
But if I come back to Miguel's comment, how do you know that the no-go theorem you get for those coupling is not related to some divergence of the Mellin transform that would not be necessary?
We can actually, for those couplings, we can actually evaluate all the Mellin integrals. There are examples, you can write examples where you can evaluate everything explicitly. That's how we check that things make sense.
Is there other questions or comments? If not, we can thank Massimo again and maybe stop at least the official discussion. I will stop the registering, and if people want to go on and discuss.